Hello everyone, my name is Elias Bachaalany. I work at Microsoft in the Security Response Center. I used to work for X-Rays before, and now I've been 1.5 years at Microsoft. I'm one of the developers of EMET, and today I'm going to talk to you about EMET internals. I'm not going to advertise about EMET, but I'm going to give a technical talk, as you'll see now. So the overview for today is I'm going to talk what's the motivation for this presentation, what EMET is and is not, a few words about it. And then we'll start breaking down EMET, how it works, so like the EMET agent in the new version, the mitigation engine, how the whole mitigation work inside EMET. We'll talk about the new feature, the crypto extension, and UI, what it does. And so by doing this, you'll understand the whole picture of how EMET is put together. I'll take questions as well at the end and also in the middle of the presentation. So here I will start with something in the spirit of the presentation by quote, which is an old Greek proverb, there's nothing hidden under the sun. And of course, as all of you are reverse engineers, you'll agree with that if you don't see this. So reverse engineers, definitely, we can't hide anything from reverse engineers. But, so I'm going to talk and explain things. So this very technical, developers will enjoy it. I'll show you some code and explain some stuff. Also hackers will like it, they want to break EMET, so I'll help them do that. We're also giving back to the community, since EMET is a result of contribution from various talented individuals and the security community. So that's one more reason. And of course, we don't want to do any security by obscurity, so you get to know how it works. And we open the door for new ideas, if you have ideas you want to share. And finally, if you're a developer, you want to write EMET-friendly code, so your code is compatible with EMET, you'll understand how you can do that. So EMET is an enhanced mitigation experience toolkit. It simply helps exploits from running successfully. It will just help doing that. It's not a bulletproof, as you'll see later on. And we employ various technologies to common exploitation techniques. And we don't necessarily need to know how the exploit works. What it is not, it's not an antivirus. We don't rely on signatures. We simply try to look up the behavior of the program as it runs. So as I mentioned before, it's not a foolproof. So it will simply raise the cost of exploitation. So like using exploitation kits and like certain modules that just generate an exploit for you may not necessarily work out of the box if EMET is deployed. It's always a cat and mouse game. We release something, somebody else says that, yeah, we broke it, so that's fine. And of course, it's easier to destroy than to build. So hacking is sometimes easier than building a robust software. I just want to make this point clear. And EMET is not effective against logic bugs, like bugs in the APIs, which can lead to exploitation. So EMET will not help in that aspect. And 4.0, we introduced what we call an EMET agent. It's a helper process that runs on your system. It handles tray icon notification. When an exploit happens, you will get a notification. It does the SSL certificate trust rule validation, event logging, telemetry. In short, it's a user mode process written in C#. It supersedes the old EMET notifier executable, which had only two responsibilities. It's not a service, so it runs with the same privilege as the logged on user, and it's designed to be pluggable. And that means all the responsibilities I mentioned are implemented as plugins that are invoked by the agent. So now I'm going to start with the mitigation engine. This is the core of EMET. So the mitigation engine is written in C++ and some inline x86 assembly. It's compiled and deployed as EMET DLL or EMET64.dll. And how it works, it starts by getting injected into the processes using an infrastructure built into the OS called Application Compatibility Infrastructure, also known as shim infrastructure. So essentially, we have a shim database. It's a database that describes under which conditions a certain DLL gets injected in processes. And this is, we registered this database, and OS will enforce those rules whenever a process is created. And the mitigation engine works with the agent. So in case we detect a mitigation, we simply talk to the agent, say report it via the tray icon, or send it via telemetry, or log it to the event viewer. And we use inter-process communication for that. What are the mitigation technologies employed here? We have DEP. It's provided by the OS, and when the process does not opt in, EMET will enforce that for the processes. We have export table address filtering, heap spray protection, SEHOP. Also, it's provided by the OS, but also EMET is a tool can act as a UI to configure that for certain processes. Also, mandatory ASLR, in case it's not provided by the OS. If you have this knowledge base missing, EMET will provide that for your processes. Reserving null page. We have a bunch of ROP mitigations. We'll talk about them in details. API behavior checks. And some hardening for things that have been broken. We also harden the protections. Let's start by DEP quickly. So if the process that did not really opt in for DEP, and you configured it with EMET, upon injection of the mitigation engine, EMET will call the API, set process DEP policy, and will either turn on or off DEP for that process. So if it's a legacy application that wants DEP, we'll simply do it from within EMET. Since the DLL gets injected in the process space, it can do anything on behalf of the process. ASLR. So EMET will bring ASLR to modules that did not really opt in for it. So they were not built with they were not linked with the dynamic base switch when you compiled it, maybe using an old compiler. So if an old DLL that was created many time ago without this switch linked, EMET will bring ASLR to that module, but only to dynamically loaded modules. So later on, when the process starts, loads an ActiveX, a DLL dynamically, this is where we enforce ASLR on that DLL. And only on Vista and up, this mitigation happens. So how it works internally? We start by intercepting calls to anti-DLL, anti-map view of section, which can be reached from one code pass is like you call load library, and when you call load library, it will eventually call anti-DLL, LDR load DLL, and end up calling anti-map view of section. So when we do that, we intercept this, and then we check the DLL. If the DLL was not compiled with dynamic base, which is this bit is set in the PE header, and the DLL has relocation table, then what we do, we revert the first step, we unmap the section, we reserve the preferred base address, and then we map the section again. And like this, the OS will be forced to relocate the DLL for you. So that we cover how ASLR is implemented or brought by EMET into your process. It's a simple trick, but very, very effective for all DLLs that do not have dynamic base bit. SAH override protection, it's also baked in the OS since Vista SP1 and on. And simply it validates the exception chain integrity before dispatching the handlers. And what is the benefit from EMET here? EMET will bring this to old OSs that do not have SAHOP. So what EMET does will re-implement the same logic in the process by using a vectored exception handler, which normally the VEH will have precedence over SEH. And so when we catch an exception, we check the current thread and we walk the chain, and we see if the chain is correct. The same logic that is in the OS, we can say we backport it to older OSs like XP and so on. Heap spray allocations. It's not provided by the OS yet. And what EMET does is simply pre-allocate or pre-reserve a certain preferred memory addresses. It's a list of the most common used addresses that exploit aim to have when they want to spray the memory. So when we pre-allocate those addresses, and I have to mention that this list can be configured in the registry. So you can configure it per process, add more memory addresses. So here, if EMET was not installed or not enabled, heap spray was not enabled, we can see like those addresses may be the ones that are preferred when the heap spray is happening. And when EMET is installed, it will break this by having this area here pre-allocated. So it won't really be the same effect when they spray the memory. That's about heap spray. Export address table filtering. What we do here, we filter any access to the export address table. And so the condition is any access to the export address table should originate from a loaded module. That means shellcode or JIT code will trigger the filter. So if you have a shellcode that tries to resolve, like implement its own version of get procedure address, so it will eventually access the export address table in certain modules. And so we use debug registers on both kernel 32 and NTDLL, and we add this debug register for read access. Anybody accessing the export address table, and the access comes from not a modules, and we trigger that protection. And so here we can see a small code snippet of the inside the source code. Like we simply add a hardware breakpoint for this module and this module. Any access to their export address table will trigger the filter in EMET. This is not really effective. This is effective against shellcode that is not really aware of EMET. So if the shellcode is not aware of EMET, it will break. But if you are targeting EMET, are aware of EMET, as you'll see here, it can be easily defeated. And DRM code have allergy against EAF, so you may hit compatibility problems if you enable EAF with DRM code. So here just a small snippet, like the shell code. Here we can see shell code trying to parse from the PEB LDR, and trying to access the EAT and so on. So this belongs to not a module. Here we can see like the segment is just shell code, is not system DLL or anything of that sort. And this will break that shell code. Bottom-up randomization as well, we reserve a set of a number of 64K regions with virtual alloc to make future memory allocations less predictable. This bottom-up randomization now is natively supported by Windows 8. So it's no operation in EMET when used in Windows 8. Now, that's a big topic here I'd like to talk about. The ROP mitigations, they are a result of the Blue Hat 2012 from last year. EMET ROP mitigations are based on Ivan Fraterich's work. He's the second prize winner of last year. He submitted a proof of concept code and a paper. And EMET re-implements this based on the paper. It implements 4 out of 6 mitigations. And here there's a reference. You can find more about the code submitted by Ivan on Google Code. So why did we re-implement? We had certain objectives by re-implementing that. We want the ROP checks to be as fast as possible. We don't want to slow down the process. The code should be maintainable and portable, so we try to minimize the use of inline assembly. We try to minimize certain code practices so the code becomes portable and maintainable. Compatibility, we want to make sure that it's compatible with most programs that you have on your system. And we try to reuse existing supporting libraries like disassembling engine, API hooking libraries. We don't reinvent the wheel. And we use robust supporting libraries. Just to draw your attention, ROP mitigations so far are implemented only for 32-bit processes. Some general terms and premises how this whole ROP mitigation work. So we have to define what we call critical function. They are system functions that are important for the attacker to call using ROP in order to achieve second stage of code execution. For example, like returning to virtual protect. Use a ROP gadget to return to virtual protect, make the stack area executable, for example, or returning to virtual alloc to allocate executable memory. Even better, like returning to load library and load a remote DLL, and thus achieve code execution. So critical functions are the ones that are needed to achieve something important when you do ROP. And this is where we start protecting at the point of a critical section. And inside EMET, it deems 50 APIs are deemed as critical functions. So what we do with those critical functions? We hook them and we redirect them to a common stub that will do extra validations before allowing the API to execute. So we will make sure that this API is called normally and not returned into. So here, proper use of critical APIs will be allowed. So they have to be called, not returned into. So critical APIs should essentially be called from inside the normally compiled module, like using high-level compiled code can call them easily without triggering those mitigations. Let me talk a bit about the supporting libraries to make this happen. We use a disassembler library. It's one internal disassembler library. It's called MSDis. It's used by the debugger engine, like Windbag, CDB, etc. Visual Studio uses the same library. It can disassemble x86, AMD, and it's robust. So why do we need it? We need it for disassembling the code and for code simulation. We'll talk why we need code simulation in the coming slides. And we also use detours. I'm sure many of you heard about detours. It's a research project. It's very portable and robust. It's used for API hooking and binary instrumentation. But detours as it is not enough for implementing what we need in EMET. So we had to modify it in a few ways. One modification we had to do is to allow detours to give us the facility to detour multiple functions into the same target. And so we want to redirect, let's say, 50 APIs to a common function, let's say a ROP check function. And so we have made some modifications. Here we can see in the code, this is like additional stuff, like we set the pointer to the pre-code generation callback, and this will allow detours to call our function to generate more code as it's detouring. Post-code generation as well, we set up another callback, so we generate code after detours finishes generating its common detouring code. And also we can associate certain structure. Here I can also pass a context so that my callbacks receive the context and they know how to generate the code based on the detoured API. So these are vital additions to detours because we want custom stubs, not just a jump to the redirected function. We also added user-controlled copied bytes count. Normally, detours will try to copy 5 or more bytes in order to replace it with a long jump. And so we allow now, we can tell detours, hey, copy more than 5 bytes. This will help us bypass anti-trampoline bypasses, people trying to execute the prologue of a function and jumping to the API address press 5 to bypass a detoured function. So this will break it. I'll show you an example. It's not foolproof, but it will break most of the stuff. So for example, this is a common pattern we see in shellcode trying to bypass any hooks to WinExec, for example. So what they do, they execute a prologue that they have in their own shellcode and then simply jump WinExec plus 5, skipping the E9 and the 4 bytes that normally would jump to the detoured function. So this will break because after jumping plus 5, we have some other opcodes that, like we put a CC, so it will crash the shellcode. Any shellcode not anticipating this will simply crash. So here we can give you an idea. Now here in EMET, per hooked function, we randomly copy at least one instruction further. I have a screenshot. I'll show you a real example. Let's take a look now at a typical critical function that is protected. So let's talk about, let's say, as we said before, virtual unlock, as in this example, virtual unlock EX is protected. Now let's see what happens when we protect this function. The first thing is kernel32.dll, this is the original function, and we can see it has been detoured with a long jump to the guarded virtual unlock EX. So if you are returning into virtual unlock, you return, but the first thing is not the actual body of the function, but it's a jump to the guarded one. Now, if you jump plus 5 from this address, you will not really execute the rest of the function. Instead, you will hit, in this case, there is one byte here. So if you jump plus 5, you hit the CC, and this will break. Maybe if you run EMET again and inspect this, you'll see maybe 5 CCs. It depends on the random values. After the jump, what detours normally do, it will leave the rest of the function body. And so here we have the rest of the function body. So that's the first part. Now let's take a look what happens inside the detoured function. What is inside the guarded virtual unlock? This is the generated code per API. Well, this is very interesting here. So this is the protected function. It's a guarded virtual unlock. It is in allocated memory. The first thing we do, this is the generated code. We push the function ID. It's the encoded address of the API. We push all the registers. We push the flags. We push ESP. We simply will call the ROP-check function. And so this function here will be almost the same for all detoured functions, except that this will change and a few things will change. But essentially, all protected APIs will end up calling ROP-check first and then resume if no violation happens. And then we clean up the stack. We restore all the registers. We want to make sure when ROP-check is triggered, we do not mess up the program state. So we save all registers, we save the flags, and we restore them. Only if there is a violation, it will not continue afterwards. It will terminate the process. So now, after we finish the ROP checks, what happens? We continue now. We want to call the API. And so this is what we do. We re-push the parameters. We push the return address, which is where we need to continue the API, the function body. These are the copied bytes from detours. They are executed, and then we resume execution. This one will assure that we return, after the API is called, we will return to the same stub, and we continue doing post checks. And so rope check succeeded. We called the original API, and then we continue doing post checks. And now what we do, we remember the return value of the API. We don't want to lose it, so we remember it. We do post checks, and we return back to the caller. So this also is variable depending on the API. We purge as much as the API requires. So I will show you now what's inside rope check. Rope check, as I said, will do some validation. And it's written in C. So as we said, we try to minimize the use of assembly code. So it will be called before resuming execution of the original API. So in short, this is real code, some code just to give you an idea. So what we do, since we are passing the registers that we pushed as an array, we take the pointer of the stack pointer, we take the called address, we decode it using decode pointer, we take the return address. These are the most important things for us to validate if the function, the API, is returned into or called properly. And then what we do, we call a function to see if it's a banned API. If it's banned, we terminate the process. We check the stack pointer for stack pivot. We see the caller. We'll talk about all different checks and details in the coming slides. Do some special checks. Now, any violation that happens during rope check will terminate the process. Otherwise, we simply resume. And when we resume, we are returning up to this point. So rope check will succeed. We resume here, and we continue. Otherwise, rope check will fail. So as we said, if any violation happens inside rope check call, it will never continue after this point. This is the core of the protection. Now, the details will be in the next slides, but this is how all APIs are detoured. This is the stubs and the checks that happen. If I have been going so fast, by covering all the background material, I can take any questions so far before continuing. If any question? Yes, please.
When you're picking a random number of flags after the off hashing at the top of the function, how are you ensuring that you're not interrupting the middle of a function or in the middle of an instruction?
Yeah, this is the task of detours library. So it will suspend all threads and make sure like nobody but the main thread that is detouring is doing that. And it happens at the beginning of the process. And it knows how to copy a complete instruction. And so it's not really bytes. It's like bytes and rounded to the size of the instruction. Yes, please? Well, it's called bytes, but if the instruction is longer than the bytes, then we will round it to the instruction count. Yeah, of course, but they have to be EMET aware. Now, if you look in the wild, they jump API address plus 5. Yeah, plus 10 maybe, but then it depends from version to version, right? So in one implementation, you can hard code. The Prolog is common almost in all platforms, right? But if you are like taking service packs, maybe some registers change. So if you hard code this in your shell code, it may be a bit different. But as we said, it's not bulletproof. It's for the things that are seen in the wild. All of the protection you see here, you say, yeah, what prevents them from doing that? Nothing. But it will increase the cost of writing more code and more stuff and so on. Yeah. As we said, like if you start taking like plus 10, then you are really becoming function specific. So the bytes will not be the same on different versions of the DLL. But you can do that now already. You can do that and bypass EMET by that. This only to break in the wild things. So no more questions? Please? Yeah. Some antivirus will try to compete, like hook again and so on. So you have to evaluate which antivirus you're using and if it's compatible or not. Now, there are, there could be incompatibility issues. Yes? I will talk now what kind of checks we do. But first now I explain the starting point, how we start to check. Now I will explain what we do exactly. Yes, please. How do you detect the end of the function, generically? You know, it's not an easy problem, right? You have multiple return addresses. You have functions that are coagulated and like function tails. Maybe it's a common piece of code. And so it's not an easy problem. We'll try to be as generic as possible. So the basis of it is detours. So we're using detours at the beginning of the function. Let's talk a bit about the stack pivot. Now we are in the ROP check. The first thing we do, we check if the stack has been pivoted. And so the most common stack pivot gadget is like the attacker will exchange ESP with EAX if EAX was controlled, and will return. Now we won't catch this, but we'll catch when the critical API is called, we will check if ESP is changed. And so what we do, when a critical API is called, you swap ESP, and then you call virtual unlock. We catch it in ROP check, and what we do is we get the threads stack bottom and top, and we make sure it is ESP is inside that boundary. So if the stack has been pivoted, we terminate the process. So this very simple check. Of course, some will say, yeah, we can patch the TIB and so on, right? Execute more gadgets and so on. Yes, but that's extra work. Caller check. This is an interesting one. So here we will disassemble backwards. Anytime a critical function is called, we start disassembling backwards from the return address in order to make sure that that's a critical function is called. That's the return address. Once inside this function, we have the return address, which is this address here. We disassemble backwards to see if this virtual unlock has been reached via a call, not a jump or not a return. So given the return address, disassemble backwards and figure out if it's called. And if there's a call, the call should lead us back to the API. It's not just any call instruction. It should also call the API. So we make sure that the API is called and not returned or jumped into. So here, in again, a scenario where we have the contents of at ESP, we have the gadget addresses and parameters, stack pivot, return to virtual unlock. Now virtual unlock will trigger the ROP check. And most likely, since this is called via return, we can see that the next gadget here, gadget number 2, is not preceded by a call. So after we return to the next gadget, pop EBP. Pop EBP is not a call. We will then trigger the caller check. So to summarize it quickly, when the critical function is called, we capture the return address. We capture all the registers, as I showed you in the stub. We pass that registers to the disassembler library so that we can resolve indirect calls. It doesn't have to be call via the import table, call virtual unlock. It could be indirect call via registers, so we can compute those given the register values at the time of the critical function. And we heuristically disassemble backwards. Again, it's not straightforward to determine the correct previous instruction. So now, if we detect a call, the call should be calling the target. So it should not be any call. It should also lead back to the same API. So how do we do that? We have a table here with the opcode sizes of the call instructions, and we try to disassemble 6 bytes before, then 5, 2, 3, 7, until we find a call that leads to the API. And we sorted them in a way that the most common call opcode sequence will be found first before like a relative call or a register or a displacement and so on. So this is a code fragment, how it happens. Here we enter the check if previous instruction is a call. We give it the return address and the call target. This is to make sure that once we find the call, it is calling the target, not just any call. And we give the register context to resolve all the indirect calls. We pass the registers to the disassembler. And we start a for loop going over all the table, the opcode table, disassemble backwards, and then decode the instruction. If it's not a call, skip it. Here we assume that failure until success. So it failed until we really find that the caller, the previous instruction is a call and is calling the target. Only if so, we return successfully. Otherwise, if we never matched, it's going to trigger the caller check. And in legitimate cases, it will be always passing the check. So returning ROP will break under this condition here, unless you find a nice gadget preceded by a call that is calling your API and so on. But it's not as simple as just doing this check, because the compiler can generate weird code constructs. And here, for example, we have a sequence. So imagine that there is a code here inside MS-DLL. It's calling an API, a critical API. This is how it calls it. It has just like an op and jump to the API. Now the return address is the caller of this address. And if we follow the caller back, it will not lead us to the API, it will lead us here. So this will legitimately break caller check. We handle such a case here. Similarly, there are programs that detour over our detour. And this is one simple case as well. Here we have, they detoured as well. Like, for example, here's a calling in this following pattern. They're jumping. It's not really calling virtual unlock. They're jumping to it. Should we trigger a false alarm? No, we handle certain checks. So it's not a very easy problem as well for the caller checks. That's an interesting one, the simulate forward execution. Simulate execution flow. What we do is we simulate execution forward from a critical function. So you call virtual unlock. At one point, it will return. And normally in a ROP sequence, it will return to another ROP gadget. And then the gadget will return to another gadget. So we forward simulate, trying to anticipate if there will be a gadget, subsequently a gadget, or normal code. And every time we return, we have to make sure that the return is preceded by a call. Because how come you have a return if you didn't have a call? In normal cases, in code generated by compilers. So what we do here, so in the case of ROP gadgets, it's going to return, return, return. I'm going to show you here some, this is a sample memory of ESP, and we'll start returning and using this gadget set here. So here in this example, I'm going to go over this fast. Here we have the first gadget, like add ESP12, return. Nothing so far. There is no critical API. We can't catch this. He's simply manipulating registers, doing some more manipulation, more stuff, again. Until we hit a critical function, we can't do anything. And now he returned to a complete function, actually, which is very good. Because at this point here he's calling an API. So he will pass the caller check because he's calling virtual unlock. And once we are inside virtual unlock, this is the return address. It's preceded by a call, and the call leads back to virtual unlock. So he will pass the caller check. It's valid gadget. It's a complete function. But what happens in the forward simulation case, at the point here, when we call this function, we start simulating. So we simulate this. We simulate the pop. We simulate the return. Once we simulate the return, we know that in this example here, this gadget was also luckily preceded by a call. So we will not trigger. So we simulated even this. We did not execute it yet. We simulated this. We disassembled backwards. We found the call. We are silent still. Nothing happened. And we continue simulating. It returns. Now it returned. We simulate. And here we notice, I didn't include in the slide, there were no call preceding this. It will flag at this point. But assume there is a call here. We continue forward simulation. Again, there is this gadget also not preceded by a call. So we can actually simulate a bunch of instructions and detect all the return addresses from the critical function. So we have a simulator that can simulate any instruction that will manipulate the stack pointer and the frame pointer in order to detect what the return will do and where it will return to. So we forward simulate, and every time we hit a return, it should be preceded by a call. If it's not preceded by a call, that means it has been returned into, and there is a gadget, not a real function call. So we catch it in multiple instances. And here, in a normal case, the shell code, you can see it was calling virtual unlock, allocate executable memory, move the shell code to that memory, and jump to the shell code. But it was already called previously because of the forward simulation. Let me show you a bit how the simulator works. So you have to imagine we called previously here, we called disassemble, and now we have a switch case, and we have a bunch of instructions that we simulate. In this example, if we encounter a leave instruction, we simulate it. We have a control structure here for the simulation, and we emulate what would the real instruction do. So we have a variable in our simulation control, and so the leave is like move EBP into ESP, so we do the same. We have a simulated stack pointer value, and we update them. The stack pointer gets incremented when a leave happens because of the pop EBP, so we also increment the stack pointer, etc. A move is of interest to us if anything tries to touch the ESP register. In this example, we're simulating move into EBP into ESP. And so we're copying the frame pointer into the stack pointer inside our simulation control structure. And this is per thread, so you can have 10 threads. Each thread will have its own simulation control structure. Return, look at the return. The code address is updated. The simulation code address is updated from the dereferenced value of the stack pointer, increment stack pointer. So it's a big simulator here, just interested in trying to do forward simulation, tracking the stack pointer and the frame pointer, and of particular interest whenever a return happens. Now here, like the return will add 4 when we return, but if it's a return with a number of bytes to purge, we check the operand count. If it's 0, don't add anything. Otherwise, if it's return 4, return 12, we add whatever the operand is purging before returning. So it's simulating forward to detect every return instruction and check if it's preceded by a call. We have some additional API checks. For example, we have extra checks for load library, and we have extra check for any memory protection API, API that changes the memory protection, and in particular trying to touch the protection of the stack area of the current thread. So what do we do with the load library checks? We hook APIs that load the library, and we parse the pass. If it's a UNC pass, we will trigger the mitigation and terminate the process. We will not trigger this if the DLL is loaded as a resource, so there's no harm in loading a DLL as a resource, even from a remote pass. Or if a DLL did not exist on disk. We know this is not foolproof. People copy the DLL to disk and then load it. Well, if they're not, again, if they're not aware of EMET, they will break. So you have to do extra effort to bypass EMET. A memory protection change. So here, any memory protection API, virtual protect, protect-EX, lower APIs, trying to change the stack area defined in TIB will trigger the mitigation. So if you try to make the stack area executable, it will trigger. We introduced from 3.5 to 4.0 a bit more protection, like down-level API hooking, the anti-detours, and we added banned APIs. Some APIs you cannot call at all. And we also did speed improvements. So we don't, now for the down-level API hooking, we were only hooking kernel 32 functions. Now we also hook kernel base and NTDLL. So let's give you an example. Virtual unlock here is the code pass. Virtual unlock will eventually call kernel base on Windows 7 and up, and end up calling NTDLL, allocate virtual memory. So we'll hook all three of them, but we'll do the rope check only once. So if you call virtual unlock, only one time we'll check at this point. We will not check at this point, neither at this point. But if you return into kernel base immediately, we'll check it here and not check it here. And if you return into NTDLL, we'll check it at NTDLL. So we'll make sure wherever you enter those critical functions, only one time we do the rope check per call. And so here you can imagine internally we have like nesting variable where we know who's calling who, how many times, and how many times we returned, and so on and so on. So we don't want to do rope checks 3 times. This kills the performance. We only do it 1 time. Banned API is very simple. We hook the API and we redirect it to a function that terminates the process. And here we've seen an exploit calling LDR hot patch routine. We simply detour it and terminate any process that tries to call this function. We only hook this function now and make it banned. Maybe in the future we will add more things that we deem as not really popular APIs and should not be called. Speed improvement. We said we have critical functions. For example, virtual unlock is not a critical function all the time. So we evaluate the function. If the function that we initially think is critical, we evaluate its parameters, and based on how it's used, we can say, no, it's no more critical. For example, virtual unlock, you're trying to allocate non-executable memory. There is no harm in that. Whether you rope into it, whether you jump into it, it doesn't matter. You're allocating data, so we don't really do anything. We directly exit the rope checks. So for example, virtual unlock is called many times in the browser to allocate data area. So we inspect its parameters. If there's no page execute bit passed, it's no more critical, so we just exit. So here I can show you. Inside the rope check here, we have some small optimization. We have a class that parses the called function, and we give it the parameter array. And then once we parse all the parameters of the known functions, we see if it's safe. No, for example, a load DLL, if not from a UNC pass, it will bail out immediately. It's virtual unlock or virtual protect, not turning a page into executable. We directly return. So this will speed up all the subsequent 4 rope checks, caller checks, simulation, and so on. So this is the first thing we do. We downgrade the function from critical to normal function, and we don't do additional checks. That will speed up. Here I have quickly talk about the new feature, the crypto trust, the certificate trust extension, which SSL pinning, and so on. So from the side of the mitigation engine, we don't do much. It's simply an extension using Windows API. So you can look at the reference here. Windows allow you to add your own plugin into the system. So you can inspect anybody that is trying to build SSL chain trust and so on. So we implemented an extension into EMET, and we serialize the certificate and we pass it to the agent. The agent will do the checks out of process. So we don't want the EMET DLL, which is injected into the browser, to consume memory and do all the logic. So the extension is very, very simple in that term. Simply passes the certificate chain to the agent. And if you want to learn how we do the certificate chain, the pinning checks and so on, it's a high-level discussion, so I advise you to look at the blog posts. It explains what are the rules, and also the user guide will explain how we do the certificate pinning. The UI, just briefly, we have like the console and the graphical interface. All it does is rewrite the shim database. This is what tells the operating system under which condition to inject the mitigation engine or not. And it's used to, like, the UI, just general settings, write new certificate trust rules, and so on. So not much for the UI. And I take questions now if you have any questions based on the things I talked, caller checks, simulation, etc. Yes, please? Yeah, I can't answer that. Maybe some stuff, as you see, for example, a null page now is part of Win8. Bottom-up randomization became part of Win8. So, yeah, some stuff will move and be part of the OS rather than like Windows Defender and so on. So somehow EMET is like bringing experimental things first, and then the OS sometimes follow, and vice versa. So upon entering the rope check, we have a nesting variable, and we increment that variable. And so it's not global. It's a per threaded TLS variable. Yeah. And I'm surprised now. This is a good question. And you will say, well, you know, I can fool you, and I can call the API in a bad way, cause an exception, handle the exception, keep the nested variable greater than 1, and then I will completely disable that, since like that. We handle that. And so, okay, you cause an exception, we're going to reset the variable for you. So we're going to check again. Yes, please? Yeah, now in 4.0 we added telemetry, and this is something new. Yes, if you want more information, the last slide, we have contact information. We'll be more than happy to share details with you. Yes, please.
Are there any features for doing management of large deployments?
Yeah, now I didn't talk about enterprise features of it, but in the user manual, we have a section on large deployment and so on. Yes, please. Yeah. Can you repeat the last part? Like, not really. Most of what we deemed as critical, we already hook. And performance, yes, we're aware of performance. As we said, we try to downgrade the critical function to non-critical if it's used in a non-critical way. This really speeds up. Like from 3.5, we were always checking anytime virtual unlock is called. 4.0, it could be called many times by the browser. You're watching a video, lots of memory allocation happens. We don't have to do forward simulation checks and caller checks, backward disassembly. So these kind of things we try to optimize, even if it's critical and may be called lots of time. We try to avoid the checks if it's not necessary. So most critical functions we don't exclude anything. What we think is critical, we're already hooking. We can say like, let's hook all the APIs. It doesn't make sense. So only things that are valuable for ROP, like virtual memory protection change, allocating executable memory, and so on. And these are hooked. And performance, yes, we know. We do our best to make them fast. And so also you have in the UI, you have the facility to turn off certain checks for processes that you want them to perform fast. Say, I want to disable forward simulation. I want to disable ROP checks completely. So you can control and speed up the process you want by turning off certain mitigations. Did I answer your question? Okay. Last question? All right. Thank you.